Fact 4. Introduce you R squared. R squared is correlation coefficient squared, okay? And in more advanced course, they show, okay, or you say it can be shown that correlation coefficient squared is summation yi hat minus y bar squared. Yi hat is a prediction value from your regression line, okay? And the denominator is summation yi minus y bar squared, okay? Now, let's first look at the denominator, okay? Have you seen this term somewhere before? Well, you see this one here, right? What is this term? Huh? The whole thing. The whole thing is called sample standard deviation in y direction, okay? Now, if I square, what do you know about standard deviation square? Standard deviation square is what? Variance, sample variance, okay? So this term is sample variance. So you know this term here, has something to do with what? Variation, okay? So in order to explain better, let's look at the graph. Say people give you a data set, x1, y1, x2, y2, all the way up to xn, yn. And this is your x bar, this is your y bar. Y bar is the center in y direction, okay? Say a point x1, y1, you make projection on y-axis. This is y1. y1 to what? Y bar. Are you with me? This is deviation of y1 to the center in y direction, y bar. And similarly, x2, y2 projection point here, distance to the center, y2 minus y bar. So what is this term? yi minus y bar is deviation of yi to what? Center of y direction. Square it, distance squared to the center. Sum them up is total distance squared to the center, okay? And center is measured by mean. And therefore you can understand this is used, this term, okay? This term is used to measure the total variation in y direction, okay? And for that we call this term total sum of square, okay? Total sum of square. Or you just say what? SST. And it is used to measure the total variation in y direction, okay? In y direction. Okay, we just mentioned summation yi minus y bar square is called sum of square total, or you say total sum of square, SST. And SST is used to describe the total variation in y direction. Now, this term can be further written as yi minus yi hat plus yi hat minus y bar. Okay? And square, you sum them out. Minus yi hat plus yi hat. After cancellation, you still have yi minus y bar. Can you see that? Now, by high school, right? In middle school, you learn this. This is called the formula of perfect square. A plus b squared is equal to a squared plus 2ab plus b squared. So if I call this term a, I call this term b. Okay? So this is summation yi minus yi hat squared plus 2ab, right? 2ab plus what? Plus b squared. Are you with me? Okay? Now, we apply summation to all three terms. Okay? All three terms. We have summation yi minus yi hat squared plus 2 times summation yi minus yi hat times y hat minus y bar plus summation yi hat minus y bar squared. Okay? Now, let's look at the first term here. Well, I'll look at second term first. This term can be shown equal to 0. And you just memorize it. In more advanced statistics course, they will prove why this term goes to 0. Okay? And only 2 terms left. Okay, only 2 terms left. Well, I give you some intuition. Okay? They say yi minus y hat, that's a prediction error. And yi hat minus y bar, they are perpendicular, these 2 vectors. Therefore, in statistic interpretation, these 2 vectors are independent. Is that clear? But you don't need to know that much for this code, for our course purpose. You just memorize this term equal to 0, okay? When you come to more advanced course, they will explain the reason why. Now, only this term and this term left. Now let's look at the first term. yi minus yi hat, that's prediction error, residual. Okay, if you square it, what? This is what? Prediction error squared. You sum it up, total prediction error squared. Is me? And why you see prediction error? Because regression model is not perfect. It cannot explain everything. Okay? So this term is called what? SSE. SSE is what? Is from sum of square what? Error. And this is used to describe the variation in y direction that is not explained by a regression model. Remember, E means error. Error is prediction error. Why you see prediction error? Because regression model cannot explain everything. Is that clear? That's the idea. Now, this is total variation in y. This is a variation in y that is explained by a regression model. So what is this term here? This is a variation in y that is explained by a regression model. This is explained by a regression model. This is not explained by a regression model. So when you add these two terms together, they give you total variation in y. Okay? Now, this is variation in y that is explained by a regression model. So we call this is what? Regression sum of square, SSR. Okay? SSR. This is SSR. Okay? This term is SSR. Summation yi minus y bar squared. As I just mentioned, this is SST, sum of square total. And this term is used to measure total variation in y direction. And we just show you this term can be decomposed into two parts. First one is called SSE. How you remember this? E means prediction error. Yi minus what? Yi hat. That's prediction error. Is that okay? So, total prediction error square, we use SSE to measure variation in y that is not explained by regression model. Right? Very easy to remember. E means what? Error. Prediction error. Why you have prediction error? Because regression model is not perfect. It's subject to what? Error. Is that okay? That's the way how you remember it. And if this is total variation in y, this is variation in y that is not explained by a regression model. Then this term is variation in y that is explained by a regression model. So for that, this is explained by a regression model. We call this term SSR. R means regression. Sum of squares regression. Okay? Now, by the formula we just mentioned, okay? R squared. R squared is equal to summation yi hat minus y bar squared divided by summation yi minus y bar squared. This term is what we call SSR. This term is what we call SST. Now, SST begins with the denominator. It describes total variation in y. SSR is a variation in y that is explained by a regression model. This is whole variation. This is just what? Part of it. Okay? So variation in y that is explained by a regression model divided by total variation in y. This is a fraction concept. So we say this is a fraction or the proportion of variation in y that is explained by a regression model. Is that clear? So what's R squared? It's a fraction of variation in y that is explained by a regression model. Okay? R squared, as we just mentioned, is equal to SSR, regression sum of square divided by SST, total sum of square. And this is used to measure the variation in y that is explained by a regression model. This is total variation in y. So this ratio is a fraction concept. The fraction of variation in y that is explained by a regression model. Okay? So this is what? R squared. Okay, R squared. Now, another way to look at R squared, different from this one, is we look at R squared. It's SSR over SST. But we're not going to stop here. We're going to decompose SST as two terms, sum of the two terms. SSE plus SSR. When you write like this, okay, instead of this, you look at R squared from what? Coefficient of determination point of view. And what does that mean? Let's look at A. When R squared is close to 1, that means SSE will be much, much smaller than SSR. And why is that? Very easy to understand. Say SSE is 1, SSR is 100. So look at the ratio here. SSR is 100, you put 100 here. SSE is 1, you put 1 here. SR is 100 here again. So it's 100 divided by 101. This number is very close to 1. Can you see that? So you know if R squared close to 1, this implies SSR is much, much bigger than SSE. And what is SSR measure for? SSR measures what? The variation in Y that is explained by regression model. And this is a part not explained by regression model. When the part explained by regression model is much, much bigger than the part not explained by regression model, right? When this term dominates this term, right? What can you say? Well, you say the regression is what? Very effective in predicting what? When the part can be explained by regression model, dominate the part cannot explain by regression model. That means regression model does a good job in predicting. Is that in predicting what? Okay? It can explain what? Most variation in Y. Okay? Now, look at the next one. Look at the next one. If R squared is close to 0, on the other hand, you can imagine, okay? R squared close to 0. If R squared is close to 0, that means SSE must be what? Much, much closer than SSR. Say you reverse the role. You change SSE to what? 100. SSR is what? 1. Then you find this is what? 101 and this is 1. So it's almost close to 0. Can you see that? So you know when R squared is close to 0, this implies SSE much, much bigger than SSR. But what is SSE? SSE is a variation in Y that is not explained by regression model. When the part not explained by regression model dominates the part can be explained by regression model. That means regression model is what? Useless. Okay? So simply look at R squared is close to 1 or R squared close to 0. You can determine how good is what? Efficiency in determining in what? Predicting Y. Is that clear? That's why we call this is coefficient of determination. Okay? Summation yi minus y bar squared. As I just mentioned, this is SST, sum of square total. And this term is used to measure total variation in Y direction. And we just show you this term can be decomposed into two parts. First one is called SSE. How you remember this? E means prediction error. Yi minus what? Yi hat. That's prediction error. Is that okay? So, total prediction error squared, we use SSE to measure variation in Y that is not explained by regression model. Right? Very easy to remember. E means what? Error. Prediction error. Why you have prediction error? Because regression model is not perfect. It's subject to what? Error. Is that okay? That's the way how you remember it. And if this is total variation in Y, this is variation in Y that is not explained by regression model. Then this term is variation in Y that is explained by regression model. So for that, this is explained by regression model. We call this term SSR. R means regression. sum of squares regression. Okay? Now, by the formula we just mentioned, okay, R squared R squared is equal to summation yi hat minus y bar squared divided by summation yi minus y bar squared. This term is what we call SSR. This term is what we call SST. Now, SST begin with the denominator. It describes total variation in y. SSR is a variation in y that is explained by a regression model. This is whole variation. This is just what? Part of it, okay? So variation in y that is explained by a regression model divided by total variation in y. This is a fraction concept. So we say this is a fraction or the proportion of variation in y that is explained by a regression model. Is that clear? So what's R squared? It's a fraction of variation in y that is explained by a regression model. Okay? Summarize from what we just covered. Okay? Suppose we want to predict y. Two different cases. When you don't know x and when you know x. What happens if you want to predict y but you don't know x? You have no choice but you use what? Average y or y bar. But when you know x, you are not going to use what? Average y or y bar. You're going to use what? Y hat. You're going to use regression line to make the prediction. So in these two cases, what will be the prediction error? The actual value is y. The predicted value is y bar. So the difference y minus y bar is prediction error. But if we know x, the prediction error will be what? Y minus y hat. Tell me, which number you think is smaller what? Prediction error. This term or this term? When you know better, you predict what? Better. Am I correct? When you know x, you will predict better. So this one suppose have what? Smaller prediction error. Are you with me? Now, let's move on. What is total prediction error? Suppose every class student, we don't know what their midterm, and we want to predict its final. We use class average final. Is that okay? In this case, yi minus y bar is what? Prediction error. Square, prediction error square. Sum them up, total prediction error square. Okay? Now, how about the situation when we know x? We are not going to use class average y, right? Average y. We're going to use what? Regression line to make the prediction. So in this case, it's yi minus yi hat squared, sum them up. Okay? Now, question. Question. Which term is smaller? This is smaller or this is smaller? Is the total prediction error squared? This is smaller? Or this term is smaller? Well, based on what we just discussed, we know if you know more, you predict better, right? So this one we're going to see what? Smaller total prediction error square, okay? So this one is smaller. So this term is at least what? Greater or equal to this term. So based on that observation, let's look at second point. Summation yi minus y bar minus summation y minus y hat squared. We say this is smaller, so the difference should be what? Difference should be greater or equal to 0, okay? So this is what? This is total prediction error. This is total prediction error when we don't know x. This is total prediction error squared. This is total prediction error squared when we don't know x. This is total prediction error when we do know x. The difference must be greater or equal to 0. But what is the meaning of the difference? This is bigger, this is smaller. So the difference means it's a reduction in prediction error due to what? due to knowing x. When we know x, we can use regression line. When we use regression line, it predicts better. So we can say this is reduction in prediction error due to knowing x, or we say due to regression model is what is used. Now, what is this term here? This term is SST. And this term is what? SSE. So this is actually what? SSR. Regression sum of square. So another way to see regression sum of square is it is what? Reduction in prediction error due to knowing x. Is that okay? You want to copy? This is third interpretation or third point of view about R squared. R squared we know is equal to SSR over SST. But third point of view, we're going to change to what? We're going to change to SSR, we're going to change to SST minus SSE, because SST minus SSE is SSR, and divided by SST. But SST is what? Total variation in y direction. And how about this? This is the reduction in prediction error due to knowing x. Is that clear? So this ratio again is a fraction or proportion concept. And that proportion is the proportion of the prediction error. That can be reduced by what? By knowing x. When you know x, you can use regression line to make predictions, so you will predict better. Therefore, there is a reduction in prediction error. Is that clear? You want to copy? Go ahead. Fact 4. The square of correlation we call R squared is a fraction of the variation in y, value of y, that is explained by least square regression line y on x. This is something we explained already. Now, the square of correlation is called the correlation coefficient of what? Of determination. I think I covered this already in my notes. And the coefficient of determination is SSR over what? SST. Is that clear? Now, it's a variation in y along the regression line as x value. It's a total variation in y. Now, this is also equal to the fraction of the variation in y that is expressed by least square regression y on x. And that's also equal to what? The ability of a regression line to make prediction known as proportional reduction in error. Abbreviation is PRE. Okay? And the proportion of the prediction error, that is, can be explained by knowing what? This is what we just covered. By knowing x. If you tell me more, I can use regression line to make predictions. Okay? Therefore predicts better. Now, let's move on. Okay? Now, we show you already SST is equal to what? SSE plus SSR. But what's SST? Is total variation. Total variation in what? What's SSE? Is variation in y that is not explained by regression model. And what's SSR? SSR is variation in y that is explained by regression model. Okay? And the bottom of this page is summarize what I put on the board not very long ago. Okay? When you not knowing x, you knowing x. When you're not knowing x, you use what? Average y to make prediction. If you know x, you use y hat. Okay? And this is prediction error. This is what? Sum of square. SS total and SSE. So the difference is what? SSR. This is something I covered already. Okay? Now stop. Proportional reduction in prediction error. The way I see from this one is SST minus SSE. And this is SSR. Are we see? Now why we write like this? This is a total prediction error. This is what? The prediction error due to knowing x. So the difference is what? Reduction in prediction error due to knowing x. Okay? Divided by SST, that's PI. Or you can look at R squared as SSR over SST. But you write SST as SSE plus SSR. That's what I explained earlier. Okay? If you write your formula like this, it's called what? Coefficient of what? Determination. Because simply look at R squared, you know how effective is your regression line in predicting what. Now when R squared is close to 1, what can you say? You say SSE is much, much smaller than what? SSR. So this means what? Regression is what? Effective in predicting what? Now, if R squared is close to 0, that means SSE is much, much bigger than SSR. SSE is what? SSE is prediction error, right? This is a variation in Y that is not explained by what? By regression model. That's why you see prediction error. SSR can be explained by regression model. When cannot be explained by regression model, dominates what? The part can be explained by regression model. What can you say about regression model? You say regression is what? You say regression is useless. Okay? Now, let's look at question number 4. What is PIE in Jones' case? Answer is R squared equal to 0.99A squared. That is 0.996. Thus, 99.6% of error in predicting Jones' height is reduced by taking his what? His age into account, okay? Or we can say 99.6% of variance in Jones' height is explained by his age. So you tell me the age, I can predict his height very accurately. Is that okay? Now, next one. The coefficient of non-determination, we call 1 minus R squared. The complementary quantity, 1 minus R squared, is called the coefficient of non-determination. That is proportional variance in Y that is not explained by X. And in our case, 1 minus R squared is SSE divided by SS1, SST. In Jones' case, 1 minus R squared is 1 minus 0.996 equal to what? 0.004, which is 0.4%. Thus, only 0.4% of variance in Jones' height is not explained by his age. Okay? Now, done. A residual is the difference between an observed value of response variable and what? The predicted value. And that is to say residual is observed Y minus predicted Y, or you say Y minus Y hat. We call this is prediction error. Say this is the data set given, okay? X column, Y column, okay? And from what we did before, we find average X is 4, average Y is 5, standard deviation is 2, standard deviation Y is 2, and the correlation coefficient is 0.55. This one you can find very easily, okay? Based on these 5 numbers, you can find what? Regression slope is 0.55. Because standard deviation X equal to standard deviation Y, therefore correlation coefficient equal to regression slope, okay? And Y-intercept, you use the formula, Y bar minus what? BX bar. Y bar, average Y is 5, minus B is what? 0.55, okay? Times X bar is what? 4. Average X is what? 4, okay? What do you get? You get 2.8. That is to say, for this data set, the regression line is Y hat equal to 2.8, this is Y-intercept, plus 0.55x. This is our best prediction line based on these square criteria. Now, look at the table here. How we get 3.35 is obtained by plugging what? X equal to 1. Y hat, evaluate when X equal to 1. That is 2.5 plus 0.55 times what? Times x is 1. And that number is 3.35. So this number is 3.35. So what is the prediction error? Error is what? What you observe. What you observe is 5, okay? Minus what you predicted. You predicted 3.35. And the difference is 1.65. That's why you find prediction error here is what? 1.65, okay? Now, prediction error squared. 1.65 squared, what do you get? You get 2.7225. And that is this number here. Is that clear? Are you with me? So if you follow the same procedure, you can find out the prediction error for what? You can find this is E1, you find E2, you find E3, you find E4, you find E5, you find E6. The funny thing is, when you add those numbers up, what do you find? You find sum of prediction error equal to what? 0. Let's check. 1.65 minus 2.45. Now look at minus 2.45 minus 1.55. It's minus 4. Minus 4, then add 1.35 plus 1.65 is 3. 3 plus 1 is 4. So 4 minus 4 is what? Is 0. Do you see that? So overall prediction error is 0. And what is prediction error squared? You square everybody, and add it up is what? 13.95. Okay? Now, this number is very important in the sense that this is a proof why least square regression line is the best prediction line, because it has what? The smallest overall prediction error square. And that number in this data set is 13.95. Okay? Comment 1. Any prediction line that passes through the point of average, x bar, y bar, will have what? Overall prediction error equal to 0. Okay? Now, comment 2. Why the regression line is the best prediction line? The answer is very simple. Since it has the smallest one, overall prediction error square. In our example, this number is 13.95. Now, how can we show it? I show it by giving you what? By giving you another example. Suppose I use another line, okay? This is also a good prediction line. The slope is 0.5, the y-intercept is 3. So this line, if I write it down, this line is, say, y eta equal to 3 plus 1, 0.5. Okay, this is a line. And you can see, when x equal to 1, you plug in what? Well, 0.5x, I forget to put x, okay? When I put x here, x equal to 1. 1 times 0.5, 0.5, plus 3 is what? 3.5. So you can see this is 3.5. Can you see that? This is 3.5. And 5 minus 3.5, what do you get? You get 1.5. You see that? Are you with me? And if you add all the prediction error, what do you find? You find sum of the prediction error is also equal to 0. Why it's also equal to 0? The idea is very simple. Look at here. If you plug in what? X bar equal to 4. 4 times what? 0.5 is 2. 2 plus 3 is 5. So this line is also goes through what? X bar, Y bar. Are you with me? So this is another good prediction line because it also passes what? The center of the data set. So we follow the same procedure as what we did before. We have all the y hat, or we have all the y eta, okay? Y hat 2. And then we find the prediction error equal to 0. And we find overall prediction error squared. What do we find? We find this number is 14. And you know 14 is what? It's greater than what? 13.95. Is that clear? This is the proof. Any other line, even it's a very good prediction line, its overall prediction error will be definitely bigger than what? 13.95. For that reason, least square regression line is the best prediction line because it has the smallest one, overall prediction error square. Is that clear? And for this data set, that is 13.95. Is that clear? The mean of the least square residual is always equal to 0. Why is that? Because we know summation x, no, summation what? Summation EI divided by n. This is mean of residual. Because summation EI is always equal to 0. So 0 divided by n, of course, this is what? 0. Is that okay? So mean of residual is always 0. Now let's look at residual plot. A residual plot is a scalar plot of the regression residuals against the explanatory variable. Residual plot help us to assess the fit of a regression line. After carrying out a regression, statisticians often graph the residuals. If the residual plot shows what? A pattern. The regression may not have been what? Appropriate. Is that okay? And from the paragraph, you understand why people draw the residual plot, because it can be used to what? Assess the fit of the regression line. Okay? Now this is the one we just did. Okay? We just did. Let me remind you. Look at here. When x equal to 1, what is the prediction error? Well, look at here. When x is 1, the corresponding prediction error is 1.65. Do you see that? Okay? So you put 1.65 here. And when x is 3, what's the prediction error? When x is 3, what's prediction error? Prediction error is what? Minus 2.45. So this is minus what? Minus 2.45. Is that clear? Are you with me? And when x is 4, it has two prediction error. When x is 4, right? One prediction error is 1, the other one is 0. Okay? So one is 1, the other one is 0. Are you with me? You plot the point one by one, you get residual plot. Okay? And why we plot the residual plot? Well, residual plot help us assess the fit of the regression line. Is that okay? Let's stop here. I'm going to introduce you what? Good residual plot. When I say good residual plot, what does that mean? This means the plots suggest that regression line is appropriate. The regression lines are appropriate for the prediction purpose. And bad residual plot, what does that mean? When I say bad residual plot, bad means the plots suggest regression line are not appropriate for the prediction purpose. Okay? Appropriate and not appropriate. Okay? Now, let's look at a couple of graphs. For example, one. Okay? Look at the first graph. This is x, which is what? Explanatory variable. And E is prediction error, not like a scalar plot. Scalar plot, the horizontal axis is what? Is y. But for residual plot, vertical axis is what? Prediction error, y minus y hat. Okay? Now, tell me if this is a good residual plot or bad residual plot. This is equal to 0. Good or bad? Think about it, okay? What's your guess? I think a lot of people will say what? It's bad, right? But the answer is what? This is no good, this is no bad, okay, either. This is what? This is wrong. Why we say this is wrong? Because look at here, the vertical distance, summation E1 plus E2 plus E3 plus E4, this won't be equal to 0, so that's wrong. If your computer generate a graph like this, you should throw that computer away. Something very wrong with the computer, is that okay? Because summation EI should equal to what? Should equal to 0. So this is not good, this is not bad, this is wrong. You should never see this, is that okay? You should never see this. Look, more examples, okay? Let's look at more examples. Look at this picture here. Is this picture good or bad? Good or bad? Some people say good, some people say bad. What's the answer? The answer is what? The answer is bad. Okay? Why this is bad? Since as x increase, the size of the prediction error also what? Increase. Is that okay? Look at here. When x level is small, you expect to see what? Smaller prediction error. When x is big, you expect to see what? Big prediction error. Okay? This suggests the regression model can only be used when x level is what? Small. Is that okay? So this is bad for the prediction purpose. If you really want to use it, you can only use when what? X level is small. Okay? Let's try the other one. Okay? Look at this. This residual plot. Is this good or bad? Answer is what? It's bad again. Why this is bad? The reason is as follows. This is bad since we see there is a pattern. That pattern is like a sine function or cosine function, some trigonometry function. Is that okay? So this is bad because you see what? You see a pattern. Is that okay? This is bad. Now, after I show you what? Two bad ones, or one wrong one, right? The first one is wrong. First one is not good, not bad. It's simply wrong, right? And these two are bad. People may ask, well, Scott, can you show me a good one? What is a good residual plot should look like? Now, next, I'm going to show you a good residual plot, okay? The good residual plot should look like this one here. Okay? A good residual plot should look like what? The following. Look at the graph. This is vertical axis, the prediction error. The horizontal axis is x. And this is E equal to 0. Okay? And these two bands is about what? Equal widths. Is that okay? And observations are randomly scattered around what? Around them. Okay? So a good residual plot. Well, you may see one or two what? Fall outside the band, but that's fine. Is that okay? One or two is fine. As long as you don't see too many. Okay? One or two is fine. Now, a good residual plot should look like this. No patterns, no trends. Randomly scattered around the line E equal to 0, right? This is E equal to 0. And randomly scattered around it, okay? Are you with me? And second one, it should be homostatic. Homostatic. Homo means the same, static means what? Degree of scattering. Should be the same degree of scattering. So that means as x increase, when x level increase, the size of the prediction error remain what? The same, okay? That's called homostatic. That's called homostatic. Should remain the same. Is that it? That's a good residual plot. Now, the one I showed you before, this one is bad in the sense that the degree of scattering is not the same. This is what? This is what we call heterozygotic. Okay? The degree of the size of what? Prediction error is not the same for what? Different level of x. So this is not a good residual plot. Is that okay? Now let's look at the next topic. Homostatic versus heterostatic. When all vertical stripe in the scalar plot similar amount of spread, the diagram is what? We call the diagram is homostatic. And the prediction error are similar in size all along the regression line. When the scatter plot is heteroscedastic, the prediction error are different in different parts of what? The scatter plot. Okay? Football shaped scatter plot are what? Are homostatic. That's why we keep saying what? Football shape. It's good for prediction purpose. That is to say. Okay? Now next one, let's flip to the next page. Okay? Let's look at the next page. Now let's read through the paragraph. Outliers and inferential observation in regression. And observation is inferential for a statistical calculation. If removing it will markedly change the results of calculation. The results of a statistic calculation may be of little practice use if it depends strongly on a few inferential observations. Points that are outliers in either x or y direction of a scatter plot are often inferential for correlation. Points are outlier in x direction are often inferential for least squared regression. Okay? Let me put regression here. After reading the paragraph, you may feel surprised, okay? Why in correlation? In correlation, outlier in either x and y direction are inferential, but regression usually only what? Outlier in x direction are inferential, but not outlier in y direction. Let's explain this, okay? This concept is very important, so let's take a close look. Look at the correlation formula. Correlation is what? 1 over n minus 1 summation xi minus average x divided by standard deviation x times y minus average y divided by standard deviation y. Now, outliers in either x direction or y direction, say x direction. If there's outlier, what happened to average x? It will affect what? Average x a lot. Affect what? Standard deviation a lot. Therefore, with that point or without point, with the point or without the point, correlation will change a lot because it changes a lot. Average and standard deviation is very sensitive. For the same analysis, same thing, outlier in y direction will affect what? Average y and standard deviation y dramatically. So outliers in x direction and y direction are both what? Inferential. But the case in regression is a little bit different, okay? So this one requires your full concentration. Let me stop here. Let's take a break so you can what? Come back to learn the new stuff. Be careful, okay? In regression, most of the time, outlier in y direction is not inferential. You see what? Outlier in x direction is inferential. Say people give you a data set, x1, y1 up to xn, yn. You make what? Scatter plot. You find scatter plot is football shape. So you're going to fit the data set with a line and say this is a regression line, okay? And this regression line is determined without point what? A, B, C. And we're going to add a point each time to study how it affects what? How it affects the regression line, okay? The first case, when you with or without A, okay? You don't have B, you don't have C. You have only A. Now, this is football shape scatter plot. This is best PT line. And when you add A to the graph, how are you going to affect the regression line? The answer is what? Little change, almost no change in regression line. And therefore, a big prediction error in A. And why is that? Look at here. When you add A to the data set. Now, the idea of what? The regression line is try to minimize the overall prediction error. So this line can move up. But can it move up to here? Of course not. If it moves to here, then every point inside the scatter plot has what? Big prediction error. Is that okay? So you cannot move towards it. Since you consider overall prediction error, this one can move only a little bit, almost no move. Is that okay? Therefore, the point to the line has a big big prediction error. We call what? A big prediction error, or you say residual. This is impact with A or without A. Now, second one, with or without B. Okay, look at second picture. With or without B. With or without B. Little change in regression again. Look at here. This line is actually very close to what? Regression line already. Am I correct? You don't have A, you don't have C. You add B. What happened to the line? Well, it just changed a little bit. Almost no change. Is that okay? Because the point is what? Very close to regression line. So little change in regression. So both A and B are not influential because no change in regression line. Is that okay? Almost no change. Now, the one is influential is the last one. Okay? With or without C. You don't have A, you don't have a B, you have only C. When you add C, what happened? The line will be attracted towards C to minimize what? The vertical distance to C. Are you with me? This is very much feasible. Why it's feasible? Let me explain to you, okay? You can move towards what? Move towards the point. And that's feasible. Why it's feasible? Before a point is here, okay? You may say, well, Scott, if you rotate towards what? C. Huh? The distance will be, originally it's here. Now it's what? Increase the vertical distance. But you don't worry about it because the other side, this one will be minimized. Before it's what? To here. Now it's only to here. It's shorter. Is that okay? The one increase compensate by what? Its counterparts. Same thing here. A point here, if you rotate to here, it looks like the distance to the line become bigger. But the point on here, the distance become what? Shorter. Is that okay? So you don't need to worry about line inside what? The football shape. All you need to worry about is the line that close to C that minimize the vertical distance to C. Is that okay? People may say, well, Scott, why don't you use argument to the point A? Well, as you can see, regression line always goes through what? The center. Are you with me? It's like a fixed center. You cannot change the center. So by rotating the line, you cannot change what? You cannot change the vertical distance. Is that clear? But C is different story. By rotating it, you can minimize it. Is that clear? But not A, because regression line, remember regression line always goes through what? Goes through the center. It's like this point is fixed. You cannot change this point. You can only rotate like this. Is that okay? So vertical distance won't change. You understand what I'm saying? So let's look at the bottom. With or without C, big change in regression line because you rotate it. Make the line close to what? To C. Okay? And since point C will attract the line towards it, slope change means what? The way how you rotate Y to X also change. Is that okay? That's why it's what? It's influential. Is that okay? So in this picture, in this given picture, A, B are not influential. Only C is influential. Is that okay? So regression usually only what? Outlier in what? X direction is influential. But in correlation, both what? X and Y outliers, they affect average X, average Y, standard deviation X, standard deviation Y. So in both directions, they are considered what? Influential. Is that okay?